My name is Gio Papio, and today I'll be discussing how raising concentration of hydroponic nutrient solution can improve spinach plant growth in low pH. First, I want to look at a little background of U.S. spinach production. Back in 2016, approximately 47,500 acres of spinach was harvested in the United States alone, and nearly all of that production was done in an outdoor setting. Most of the spinach came from California. In fact, about 65% of it did, while the remainder came from areas of Arizona, New Jersey, and Texas, altogether accounting for about 98% of spinach production. And looking at this graphic, you can see that because spinach comes from only these four places, it has to travel across the United States in order to reach your local supermarket. And this can lead to a shortened shelf life as well as increased transportation costs. Switching lenses a bit and looking now at hydroponic production, there are many benefits involved with producing in this way. First, hydroponics allows for year-round production as well as local production. By producing year-round, you can drive down costs during the off-season, and by producing locally, costs can be driven down through lower transportation as well as increased shelf life in supermarkets. Additionally, people nowadays like knowing where their produce is coming from. Hydroponics also allows for an increased precision in environment, and this can optimize your conditions, leading to an increased yield in your produce. And another benefit is that hydroponics allows for increased land and water use efficiency, thus driving down your environmental footprint. However, like any other system, hydroponics has its own set of challenges. One being the incidence of waterborne diseases, specifically that of Pythium species. There are several known methods to offset these diseases, one being the use of chemical agents. However, with hydroponics, chemical agents can either be very limited or quite costly. Water chlorination is another option, but with water chlorination, there runs the risk of chlorine and chloramine toxicities for your plant. UV radiation can also be used, but with UV radiation, this can lead to the elimination of both harmful and useful bacteria. Pasteurization has also been used, though with pasteurization, this high temperature required for it can lead to precipitation of calcium salts. Sonication is another option, but with sonication, it requires a lot of very expensive parts. Ozone microbubbling has also been investigated. However, with ozone microbubbling, this can lead to reduced plant growth due to osmotic stress. And lowered water temperature is also a possibility, but lowered water temperature can lead to reduced production capacity. One method that we looked into a little bit deeper was using low pH for disease reduction. It's been found that diseases are optimized between pHs of 5.5 to 6.5. And this is problematic because that same pH range of 5.5 to 6.5 is also optimal for most plants. It has been found, though, that at lower pH, like below 5.0, disease incidence can actually be reduced. Looking at basil, we actually found through previous research that basil growth was one plant that is unaffected by changes in pH. And you can see in this picture that basil growth at pH 4.0 compared to a pH 5.5 look very similar to each other. It was found, though, that there was a reduction in the nutrient concentration. It just did not lead to any deficiencies in the growth itself. This made basil an ideal candidate for an inoculation study using Pythium ephanedramatum. And it was found that at pH 4.0, Pythium disease was successfully suppressed, thus offering an effective yet low-cost solution to managing Pythium. And you can see that here, comparing the pH 4.0 inoculated with the pH 4.0 non-inoculated roots. These both look very healthy and strong and comparable. Meanwhile, at pH 5.5, you can see that the non-inoculated roots look quite healthy, while the inoculated roots at pH 5.5 show clear signs of disease. A similar study was conducted on spinach, and it was found the effects were quite different. and spinach growth was reduced by lower pH. Looking at this graph, you can see this, that at pH 4.0, spinach grew at about 1 gram per plant. Meanwhile, at pH 5.5, spinach growth was approximately 8 grams per plant. So at pH 4.0, both the spinach roots and shoots showed stunting, and you can see that right here. Meanwhile, at pH 4.5, you can see that the roots at pH 4.5 and the roots at pH 5.5 are very comparable to each other, and the shoots at pH 4.5 look only slightly reduced. And looking at all of these, it's likely that at pH 4.0, this reduction in growth was caused by pH itself, as in the acidity of pH. Meanwhile, at pH 4.5, this growth reduction is likely due to pH-related factors, for instance, nutrient competition that may lead to a limited nutrient uptake. Moving on to a chemical analysis of the spinach plants, it was found that uptake of nutrients was limited in low pHs. And looking at the 5 representative nutrients, you can see that at pH 4.0, the concentration of each nutrient was the lowest, and then it grew from there until it reached its maximum at pH 5.5. So with this in mind, we came up with a hypothesis that increasing nutrient concentrations will increase nutrient uptake and thus improve spinach plant growth in low pH environments, specifically 4.5. And we came up with the following objectives. First, we wanted to determine how spinach plant yield is affected by pH as well as nutrient concentration changes. Additionally, we wanted to determine how nutrient uptake is affected by the same pH and nutrient concentration changes. Looking at our methods, we made a 2x2 factorial experiment, randomized complete block design with 2 trials and 4 replications in each. In this, we compared pH treatments of 5.5, which was our control, versus the reduced 4.5. And then looking at the nutrient solution concentration treatments, we compared a raised 3.4 decisiemens per meter with our conventional 1.4 decisiemens per meter solution. This trial was conducted in a deep water culture system where each bucket was its own hydroponic system and 1 experimental unit. And we used the cultivar Core Vert spinach. This was done in a growth chamber with a day temperature of 25 degrees Celsius and a night temperature of 15 degrees Celsius with a light intensity of 350 micromoles per meter squared per second. After 20 days of growth, the spinach was harvested and measurements were taken for the yield. We found that at pH 5.5, the treatments were not significantly different from each other. And you can see this highlighted in blue with these 2 pH 5.5 treatments compared to each other. Meanwhile, at pH 4.5, which is highlighted in red, these treatments were significantly different from each other. Looking now at the least nutrient analysis of these spinach plants, we decided to picture these 4 representative nutrients to show the general trends of all 16. And we found that calcium, copper, potassium, magnesium, manganese, phosphorus, sulfur, and zinc all showed reduced uptake in the pH 4.5 EC 1.4 treatment when compared to that of the conventional treatment. Upon increasing the EC, so in the pH 4.5 EC 3.4 treatment, calcium, copper, potassium, manganese, phosphorus, and sulfur all showed a similar leaf nutrient concentration when compared to the conventional treatment. However, with magnesium and zinc both below, you can see that there was still reduced uptake at the pH 4.5 EC 3.4 setting when compared to the conventional treatment. So to discuss, we found that at pH 4.5, EC 3.4, there was a 30 to 45% increase in growth when compared to the pH 4.5, EC 1.4 setting. However, at pH 4.5, EC 3.4, there was still a 30% reduction in growth when compared to the conventional pH 5.5, EC 1.4 treatment, thus implying that additional optimization of both pH and nutrient solution are still necessary. Now, looking at the additional costs, we found that it would cost about an extra 1.6 cents per liter of solution to bring the nutrients of that at the pH 4.5, EC 3.4 treatment. Now, looking at some additional considerations, we had some questions at the end of this study. First, we were curious, is spinach acidity tolerance different looking at different cultivars? So in ours, we used the cultivar Corvair spinach, but what if we used a different? Would that change our results? And then our next question was, can other leafy greens tolerate this lower pH when given higher concentrations of nutrients? For instance, if we conducted the same study with lettuce, would it be more so like that of basil, or would its results look more like spinach? With that, I would like to thank all of the following people who helped make this project a success, as well as our funding source at the USDA. And if you have any questions, please feel free to contact me. Thank you.